and A2 is B, and everything else is empty. Then this is the same case, right? Because A union, B union, everything else is same as A union and B union, A union B. So this comes from right from the axiom. So by definition, this law of addition holds. So law of addition. But this does not hold always. We need this condition. Okay? There must be disjoint. Alright. So using this conditional probability, we derive a useful theorem. Before that, we define partition. Partition Okay. Let's say we have again a measurable space. Then a subcollection of F. Let's say C1, C2, and Cn. Subcollection of F. So remember, this F sigma algebra is a set of subsets of omega. So the elements of F are subsets of omega. So when we say subcollection of F, that means C1, C2, up to Cn, they are subsets of omega, which are also elements of F. Okay, so we pick part of F to define this subcollection. And this subcollection is called a partition if they are disjoint, mutually disjoint. When K and L are different, their intersection is empty set, and together they add up to entire omega. Okay. CK. So if we take the union of all of these, we can recover the entire omega, but they are mutually disjoint. Okay. So this is mutually disjoint. And this property we say collectively exhaustive. So that means collectively means together, and exhaustive means it covers entire omega. So collectively covers entire omega. So we say collectively exhaustive. So if this collection is mutually disjoint and collectively exhaustive, then this collection is called a partition of omega. Okay, so intuitively, this is like this. So here's omega. Let's see, it's a little ugly. So it's omega. Okay, so here's omega, and we divide this entire space into a collection of disjoint subsets. Okay, something like this. So C1, C2, C3, C4, and so on, Cn. So none of them overlap with each other, with other subsets, And if we take all of them together, they cover entire omega. So that's what a partition means. Of course, there can be many kinds of partitions, but any partitions must satisfy these two conditions. Okay. Here's one example. Very simple example. Let's say S is a set of all UBD students. And define two subsets of S. Okay. So pick a student and S is male. So male students. And F, S is female. Then the collection of these two subsets is a partition of S, right? Because there are no student who is male and female at the same time, so I guess so, but yeah, so it's empty set. So the intersection is empty set. And also the union of male students and female students covers entire set of students, right? Otherwise, there must be some student who is not either male or female, but I don't think there are such students here. So it covers entire S. So this is mutually disjoint and collectively exhaustive. So this collection is a partition of S. Okay. Now, using this concept of partition, let us derive a useful theorem called Partition Theorem. Or it is also known as the law of total probability. Okay, let's say omega F and PR is a probability space. So again, I repeat, when we say probability space, this is a probability space. That means this F is a collection of subsets of omega that satisfies the axioms of sigma algebra. And this PR is a function from F to real numbers that satisfies the axioms of probability measure. Okay? Every time we introduce this, we cannot say, it's very cumbersome to say this satisfies these axioms and this satisfies these axioms and so on. We just say this is a probability space and that's it. So it is understood. Okay, so that's why we define these terms. It's so convenient, economical. Okay, so this is a probability space, and let's say B1, B2, and so on, Bn is a partition of omega. Okay, these are assumptions. Then for any event, so A is an event, we have this probability of A is equal to the sum of conditional probability of A given Bk times probability of Bk. Okay, so let's prove this. Since these Bk's are a partition of omega, we have this equality. Omega is equal to the union of Bk's, because a partition is collectively exhaustive. So if we take the intersection with A, both sides, we have A union omega on the left hand side. We have A union of this union, A intersection and this union. Okay, but this left hand side is equal to A, and this right hand side is equal to this union. So each of Bk will intersect with A, then take union. Okay, so this is distributive law of union and intersection. So we take intersection with A with each of Bk's, right? So this A intersect this union is same as union of A intersection Bk. Okay, so this A is equal to this. Now, again, since Bk's are a partition, they are mutually disjoint. So Bk intersection Bl is empty if K is not equal to L. But look at this one. Now, A intersect Bk intersect A intersect Bl is equal to A intersect Bk intersect Bl. But this is empty set. So A intersect empty is equal to empty. So that means this intersection and this intersection, they are mutually disjoint. Okay. So that means since they are mutually disjoint, the probability of this, so this is a disjoint union. Disjoint union. So this is a disjoint union. A cap B. From the axiom 3 of probability measure, disjoint union can be expressed as the sum of probabilities. No,